This is the last video for my differential equations class, and now we're going to talk about non-homogeneous systems. We're still going to be solving systems of differential equations, but this time the equations will look like this. And f will be, maybe it'll be a constant vector or it'll be a function of t, whatever the case may be, f will not be equal to the zero vector. So I'll demonstrate two methods like we had before: variation of parameters and undetermined coefficients. So let's start with undetermined coefficients. For this example, let x arrow prime equal 5, 9, negative 1, 11, x arrow plus 2, 6. I'm starting off with a simple one where the non-homogeneous portion, I suppose if you want to call it, this part here is not the zero vector, but it's not really a function. It is technically a function of t, but it's a constant. Each of these are constant functions, so they're really not that big of a deal. So it's an easy example to start with. First thing is we always do is find those eigenvalues. So you get 55 minus 5 lambda minus 11 minus 16 lambda plus lambda squared plus 9 equals 0. Let me go ahead and organize this to lambda squared minus 16 lambda plus 64 equals 0. This does factor lambda minus 8 times lambda minus 8, and so lambda has the repeated 0 of 8. Now let's plug it in. We'll see if we get one eigenvector, then we have to do some work. Otherwise we get two eigenvectors and we'll be able to use both of them. So let's see what happens here. Let me plug in my lambda equals 8. I'll get 5 minus 8, 9, negative 1, 11 minus 8. I get negative 3, 9, negative 1, 3. Hopefully you can see if I do negative 3 times the second row, add it to the first row, I'll be able to wipe out the first row. So I get negative x plus 3y equals 0, or let me write it as 3y equals x. And then when I make my eigenvector, I think it's easiest if I let y equal 1 and then x will equal 3. So unfortunately I only have one eigenvector. To get a second eigenvector, we'll call it p. We have to solve this equation, a minus lambda I p equals k. Let's throw those in. A minus lambda I already have up here. I have negative 3, 9, negative 1, 3. P, I don't know what it is, so I'll call it p sub 1, p sub 2. And k we already have is 3, 1. So let's see what happens then. I'll multiply this through. On the left, I'll get negative 3p1 plus 9p2 and then I'll get negative P1 plus 3p2, and that equals 3, 1. Now either one of these really doesn't matter that I can use. In fact, one row is a multiple of the other row, so I'll just go with the second row. I'll do negative p1 plus 3p2 equals 1. Now remember, p doesn't really matter. Let me go ahead and do 3p2 equals 1 plus p1. Now if I were to allow p2, technically speaking, I could allow p2 to equal 0, and then p1 would equal negative 1. But let's say I'm going to allow p2 to equal 1. So my vector p then, if I allow p2 to equal 1, then I'll have 1 plus p1 is equal to 3, or p1 is equal to 2. And so what I get then, I get my complementary solution. My k1 was 3, 1. That would be attached to e to the 8t. That's my lambda. Put a c1 in front of it. Then c2. Remember how this second one works. We take our k again. We have t e to the 8t plus then just 2, 1 e to the 8t. So that would be our complementary solution. Now let's try to find a particular solution. So to find xp, it's best to put it in the format of the answers already. The answer format, or if you will, the f portion, here, the part that comes after the plus, is 2, 6. Since I'm going to just get constants, I'm going to allow xp as a guess to just equal a constant vector. Plug it in and see what happens. So we want xp prime to equal a, which is 5, 9, negative 1, 11, the original matrix, x sub p plus 2, 6. Well, if I take the derivative of a constant vector, I get 0, 0. On the other side, then, I'm going to let xp be ab, so let me go ahead and erase this and replace it with ab. And let's see what we get. I get 5a plus 9b. And I get negative a plus 11b. Plus 2, 6. Then what I'll do, I'll take the 2, 6 to the other side, so I'll subtract it off, and I'll get a series of equations. 5a plus 9b, negative a, plus 11b will equal negative 2, negative 6. Now, in order to solve this, I'm going to multiply the second equation by 5. That gives me the equations 5a plus 9b equals negative 2, negative 5a plus 55b equals negative 30. Let me add these together. When I do that, I get 64b equals negative 32, or b equals negative 1/2. Then I can do the same process again, or I find it actually easier to plug this in and see what we get. So I'm going to take that and plug it into the second equation, the one that says negative a plus 11b equals negative 6. And let's see what we get then. We have negative a minus 11 halves equals negative 6. Let me add the 11 halves to the other side, so I get a equals negative 6 plus 11 halves. And negative 6 you can think of as negative 12 over 12. So this will be negative 1 half, and so a will equal 1 half. And then I've got my x sub p. If I want my complete solution then, I'll put my xp out front. For my second example, let's solve x arrow prime equals negative 1, 5, negative 1, 1, x arrow plus sine of t, negative 2 cosine of t. And as usual, let's find our eigenvalues first. And let me FOIL this out and see what happens. I get a negative 1. Then I have a plus lambda minus lambda. The lambda parts disappear, but I will get a plus lambda squared. And so I get lambda squared plus 4 equals 0. Lambda squared equals negative 4. Or lambda squared equals plus and minus 2i. Let's plug those into the a minus lambda I. We have negative 1. I'm going to start with lambda equals 2i. So I have negative 1 minus 2i, 5, negative 1, 1 minus 2i. Now, I've shown you before, if I try to eliminate one of these rows, it will eliminate, assuming everything I've done beforehand is correct. So instead of bothering with that, I'll just go straight to the second equation, and I will get negative x plus 1 minus 2i y equals 0. 1 minus 2i y equals x. And when I get a chance, to allow one part of the vector to equal 1 is always helpful. So for my eigenvector, I'll call it k1. There's actually two eigenvectors. We'll get y equal 1, and then my x will equal 1 minus 2i. Now that's attached to the eigenvalue 2i. So remember this. You can actually get both vectors by just doing my e to the 2i. 1 minus 2i, 1, times e to the 2i t. That'll equal 1 minus 2i, 1, times cosine of 2t plus I sine of 2t. And let me multiply it all out. I'll get cosine of 2t. I'm going to do the real parts first. Cosine of 2t. But then you have minus 2i times I sine of 2t. Let me get my cosine of 2t. When I do the negative 2i times I, I'll get negative 2i squared. So it'll be positive 2 sine of 2t. Now let me handle the I parts. I have I times sine of t, sine of 2t, minus 2i cosine of 2t. And then in the second row, I'll get cosine of 2t plus I sine of 2t. And then when you break this up into the real and imaginary parts, you'll get cosine of 2t plus 2 sine of 2t, cosine of 2t, plus I times sine of 2t minus 2 cosine of 2t sine of 2t. This allows me to write my complementary solution. Now let's take a look at the solution vector, or the non-homogeneous part of the vector here. This sine of t negative 2 cosine of t. The f part that we have is sine of t negative 2 cosine of t. Now the way you might want to think about that is the following. Perhaps you should think of it as sine of t0 plus 0 negative 2 cosine of t. The reason why I mention this is because you want to try to make your solution to be similar to this. And one way you can do this, for an xp, what I'll try is, it would not be good enough to do a, like if I try to just do this, if you try to do this, what you'll find is you don't have enough unknown quantities to get the job done. You'll end up getting a value of a on one row, and then you'll get a contradictory value of a on the second row. So instead of this, what you really want to do is set your xp equal to something a little more general, like a cosine of t plus b sine of t, c cosine of t plus d sine of t. This way you've got cosine of t times the vector ac, you've got sine of t times the vector bd. Now let's throw it in and see what happens. So we need to put it into this equation. Let's throw all of our numbers in. If I do xp prime, here's what I'm going to get. I'll get negative a sine of t plus b cosine of t, and then I'll get negative c sine of t plus d cosine of t. On the other side, what was my original a? Was negative 1, 5, negative 1, 1, and now we're guessing a cosine of t plus b sine of t, c cosine of t plus d sine of t, plus, and my f was sine of t negative 2 cosine of t. Let's multiply it out and see what happens then. On this right hand side, I have to take negative 1 times the first row. So I have negative a cosine of t minus b sine of t. But then I have to take 5 times the second row. plus 5c cosine of t plus 5d sine of t. And then I'll go ahead and do the same thing again for the second row here. I'll get negative a cosine of t minus b sine of t. And then I'll get plus c cosine of t plus d sine of t plus sine of t negative 2 cosine of t. Let me rewrite this. Now what I'm going to do is leave this vector over here, but I'm going to take everything to the left-hand side. So gather everything together in terms of sine and cosine. Let's see what we have here. I'm going to gather my cosines first. So when I add all of this stuff to the others to the left side, this negative a will become a positive a. So I'll have an a plus a b. And then I'll have minus 5c cosine of t plus, now let's gather the signs up. I'll have a positive b minus a 5d, negative a plus b minus 5d times sine of t. I'll do the same thing here. I'll have a positive a again, but a negative c. So I have an a minus c plus d cosine of t. And then for the sine part, I'll have a positive b minus c minus d. And that will equal 1 times sine of t, negative 2 times cosine of t. From this, I'll be able to get 4 equations. For example, there's no cosine over here in the first row, so it's 0 cosine of t. So I'll get an equation for the first coefficient. A plus b minus 5c will equal 0. Next, I'll get this coefficient here is equal to 1, the thing in front of sine of t. So I'll get negative a plus b minus 5d equals 1. And then I'll get the coefficient down here in front of cosine is equal to negative 2 this time. So I get a minus c plus d equals negative 2. And then finally, the stuff in front of sine is equal to 0 because there's no sine term in the second row. B minus C minus D equals 0. Now what happens next? There's no good way to sugarcoat it. If you know how to get your calculator to give you an answer to something like this, all the better. If you don't, you're going to have to do elementary row operations until it's evident what the answers should be. So for example, I'm going to make up a 4x4 matrix, and I have an A, B, and C each have coefficients, but D does not. So this first row can be translated into 1A, 1B, negative 5C, and 0D. It's an augmented matrix because I'm going to include the solution vector on the right-hand side. Next I have negative 1A, positive 1B, 0C, and negative 5D. That was equal to 1. Then I have A minus C, there was no B, plus D was equal to negative 2. And then finally 0, 1, negative 1, negative 1, 0. There's no good way to sugarcoat this. It's just you got to get down and dirty and gritty on this one. unless you know how to make your calculator give you the answer. But then again, it may not give you exact answers. It may give you decimal equivalents, which may not always be the best thing. Well, anyways, let's see if you can hang with me through all these computations. The first thing I want to do is clear out the first row except for the first column, I mean. Anything under this first term I want to wipe out. And so in order to do that, if I take the first row and simply add it to the second row, I am guaranteed to wipe out the first entry. I can do that by taking the first row plus the second row, and I write that as R1 plus R2. When I'm doing these calculations, I'm not going to affect the row that I am taking and adding to other rows. It'll stay the same. Alright, let's see what happens then. If I take row 1 plus row 2, then 1 not minus 1 will give me the 0. 1 plus 1 will give me a 2. Negative 5 plus 0 will give me a negative 5. And 0 plus negative 5 will give me a negative 5. 0 plus 1 will give me a 1. Now at the same time, I want to take this first row and wipe out as much of the third row as possible. So I'm going to target the very leading coefficient in the third row. If I take the negative of the first row and add it to the third row, I will zero out this entry. Negative R1 plus R3. So when I do that, negative 1 plus 1 will be 0. Negative 1 plus 0 will be negative 1. The negative of this, 5, plus negative 1 will be 4. And then a negative 0 plus 1 will still be 1. Negative 0 minus 2 will still be negative 2. And I have not just yet done anything with the last row. Now, what you typically do is you typically will use the second row to wipe out everything underneath and above except for the leading entry. This is what they call a pivot column, if you will. However, since it starts with a 2, in order to make it so I would be able to get rid of things, I would have to divide everything by 2, and I really don't want to work with these fractions. Lucky enough, I see this third row will make it easy for me to wipe out the things above and below it, at least in the second column. So I will work that. So what I will do is I will take the third row and simply add it to the first row. I call it R3 plus R1. So when I do that, negative 1 plus 1 will be 0. 4 minus 5 will be negative 1. And then 1 plus 0 will be 0. And then don't forget over here as well, negative 2 plus 0 will be negative 2. Now I'm also going to wipe out the second row. If I multiply this third row by 2, so if I do 2R3 and add it to R2, I'll be able to at least wipe out this particular coefficient. So with that in mind, by the way, these are going to stay zeros throughout the rest of the problem. Negative 2 plus 2 will be 0. Negative 8, if I multiply this, by 2 will be 8, minus 5 will be a 3, and then 2 minus 5 will be a negative 3, and then we have negative 4 plus 1 will be a negative 3. Of course, I don't affect the row itself. And then finally, if I take row 3 and add it to row 4, I'll be able to wipe out this leading coefficient. 4 plus negative 1 will be negative 3. 1 plus negative 1 will be 0. And then negative 2 plus 0 will be negative 2. When I did the R3 plus R1, negative 1 canceled, that canceled. I forgot about this thing right here. 1 plus 0 makes that into a 1. Notice I'm able to get C. This is where the C location is. I have negative 3C equals negative 2. C will equal 2/3. Let me go ahead and box that so I know what it is. Now, I'm going to keep going here because I want to wipe out more stuff. For example, right here I noticed if I take row 4 and add it to row 2, I'll be able to wipe out this particular coefficient and I'll have a similar situation to what I had here. So I'm going to take R4 plus R2. That's all I'm going to do right now. So all the other rows, R3 is unaffected as well. And then when I do this, the 0 plus 0 doesn't do anything, but the negative 3 plus the 3 does. And then the 0 plus the negative 3 doesn't do anything. However, over here, negative 2 plus negative 3 equals negative 5. R3 plus R4, I'm finding more errors as I go. Alright, what that means is I have to take negative R4 plus R2. So negative 3 plus 3 gave me a 0. 0 minus 3 gives me a negative 3. And I have to take negative 2, so that'll be 2 plus negative 3 will be negative 1. And that tells me there that was the D place. Negative 3D equals negative 1, or D equals 1/3. Let me box that off. Now for the rest of it, I guess I could go and try to wipe out things like this. Like I could probably take this and wipe out that particular entry there, although I really don't see it as a big deal now that I have answers for C and D. Notice here A is in terms of C and D, and B is in terms of C and D. So I'm going to stop this game. And I'll write A minus C plus D equals negative 2. And down here I have negative B plus 4C plus D equals negative 2. So A equals negative 2 plus C minus D. That equals negative 2. C is negative 2/3 minus 2/3. Minus 1/3. Well, this is really nice. This is negative 3. So A equals negative 3. Now for B, I'll go ahead and try to get it by itself. I have negative B equals negative 2 minus 4C minus D, or B equals 2 plus 4C plus D. 2 plus 4 times negative 2/3 and plus 1/3. I'm going to rewrite the 2 as 6 over 3. This here will be minus 8 over 3 plus 1 over 3. So it looks like negative 1/3. And so I have my XP. That was A cosine of t plus B sine of t. Where was my C? C was negative 2/3 minus 2/3 cosine of t. And then my D was 1/3 plus 1/3 sine of t. It's most likely that you will see your book write something like this. Most likely you'll see them write a vector times cosine of t, and then another vector times sine of t. You could even go a little further, like you could take the 1/3 out of here and do things like that. But there's absolutely no reason to do stuff like that. So our complete solution then, x, that will equal, we had c1 times cosine of 2t plus 2 sine of 2t cosine of 2t plus c2 negative 2 cosine of 2t plus sine of 2t then I had a sine of 2t, and then plus this thing. So let's see, plus negative 3 negative 2/3 cosine of t. Heck, I'll go minus 1/3, and I'll have 1 negative 1 sine of t. That is just for variety. Don't feel like you have to do anything like that. So this is the nature. If I had a 3×3, there's just more coefficients to equate. That's all there is to it. I don't see the purpose in doing a larger size matrix. So let me move on to variations of parameters. Alright, so we're going to be solving the same kind of an equation, of course. Which of these you use is just a matter of preference. Of course, the f vector will not be 0 in this case. And let's say that x sub c equals c1 x1 plus c2 x2. The discussion I'm going to use here will involve 2×2 matrices, but it does work, of course, for larger size matrices. So I'm going to let x1 equal x1 y1, x2 will equal x2 y2. Now, things we know. We know that x1 prime equals ax1, x2 prime equals ax2, because both of these x1 and f2 are solutions to the homogeneous system. I am going to allow phi, capital Phi if you will, to be the matrix that is made up of two column vectors, x1 and x2. And most likely, these x1 and x2 are the eigenvectors, so that's most likely what this phi is going to be, unless you have some sort of conjugate thing or some other strange thing. You don't get two independent eigenvectors, you simply have two vectors that you have to work with. So this is a more general situation. And this, of course, if I replace x1 with its values, this forms a 2×2 matrix. And then when I use the notation phi prime, that simply means take the derivative of every entry in the matrix. Now, when we go to x if I use these together to create myself a matrix where one column is x1 and another column is x2, like that, then it also equals a matrix whose first column is AX1, whose second column is AX2. It just so happens that I'll be able to factor out the A out of there. Remember, these are 2 entries for each of these. So what does this say then? This here, if I were to write it and it's all this elongated form, I have x1 prime, y1 prime, x2 prime, y2 prime, and that equals A, x1, x1, y1, x2, y2. And we can see that I come up with a new equation, phi prime equals A phi. Let's hang on to that for a little bit. I'll be using that a little bit down the line. Now next, just imagine this vector u, that it consists of u1 of t, u2 of t. But while I'm doing, there are functions of t, but I'm not going to bother with that because they'll just get in the way of the computations. Just keep in mind that every single thing here could be a function of t. Create what we hope will be a solution by having our phi times u. This is just like we did before. If you were to actually multiply this all out, you get x1. You would be able to break it up into a u1, this thing, u2, this column, and it's exactly the same kind of thing we did before. Now what I'm going to do is let me take the derivative of xp prime, and when you multiply this stuff out, each and every entry will be some sort of a product of items in it. So then when you take the derivative of products, you have to break it up into the product rule for derivatives. Well, with that in mind, then you'll be able to decompose these things into the following format. You will have a phi prime u plus phi u prime. So what we're talking about here is the product rule will work exactly as you expect the product rule to work. Now we also have xp prime equals axp plus f. It is, after all, a solution to the original system. Let me go and do one thing more here. xp prime. Well, let me replace this xp with phi u. A phi u plus f. And now let me go ahead. I have xp equal to this down here, and I have xp equal to this up here. So we have phi prime u plus phi u prime equals a phi u plus f. Now somewhere around here, oh, there it is. That's exactly what I was looking for. There it is right up there. See it? Phi prime equals a phi. Let me go ahead and change this phi prime to an a phi. Well, this is nice because the a phi u's cancel. So I have phi u prime equals f. Now, phi, let me come back here for a minute and talk about phi for just a second. Phi here is each of these vectors were solutions to the homogeneous system. With that in mind, they're linearly independent. So the point that I'm making is that the determinant of this matrix will not be 0. That means I can take its inverse. So let me go ahead and do that. U prime will equal phi inverse f. And you have to do that on the left-hand side. Multiplication with matrices is not commutative. So now if I'd like to get u, then as I do before, just like I differentiate component by component, I can integrate component by component. And these are all possibly functions of t. Even if they're constants, they're functions of t. Now u, let's see what u is equal to. Actually, u equals phi inverse of xp, phi inverse times xp. So I have, remember, xp so if I want that, then I'll have phi inverse xp will be the integral of phi inverse f dt. And then I can finally get my solution for x sub p to equal phi integral phi inverse f dt. Of course, you cannot pull this phi in there, and you cannot pull the phi inverse out of there because they have functions of t for their entries. This is the formula then that I'm going to use. This is the variations of parameters formula. So let's go ahead and solve or do an example. As always, we'll find our eigenvalues first. And let me go ahead and multiply it all out. We'll have -1, and then I'll have negative lambda, then I'll have positive lambda. So the lambdas go away, and I'll have plus lambda squared. And so I have lambda squared minus 9 equals 0, or lambda equals plus and minus 3. Let's go and get our eigenvectors. I'm going to have two eigenvectors here. Lambda equals 3. Let's go ahead and plug it into that matrix up there. We have 1 minus 3, 8, 1, -1, minus 3. That gives me -2, 8, 0, 1, -4, 0. Not too hard to see. If I take 2 times the second row and add it to the first, I'll wipe out the first. So I'll be able to get this to the following format. And we have x minus 4y equals 0, or x equals 4y. So for my first eigenvector, if I let y equal 1, x will be 4. For lambda equals -3, I have 1 minus -3, 8, 2 zeros for the column. -1 minus -3. I'll get 4, 8, 0, 1. Here I'll have -1 plus 3 will be 2. And hopefully you can see -4 times the second row plus the first. Wipe it out. 0, 0, 0, 1, 2, 0. X plus 2y equals 0. And I guess I'll do x equals -2y. And I will allow y to equal 1. Y equals 1, x will be -2. So I have my complementary solution, I had C1 4 e to the 3t plus C2 negative 2 e to the negative 3t. Now we form our matrix phi. So include the t's in it. So I have 4e to the 3t, e to the 3t. So there's my first column. And then over here I get negative 2 e to the negative 3t, e to the negative 3t. And then I'm about ready for my solution. Before I do anything else, I need to take the inverse of it. And it's probably not a bad idea just for you to write down how to get an inverse of a non-singular matrix like this one. But for this purpose, I'm going to put down a formula down in here. To get the inverse of a matrix with those entries, you divide by the determinant of the matrix, so that's AD minus BC. This is why the determinant can't be equal to 0, because the first thing you do is divide by it. Next thing you do is you swap these diagonal terms, so the A and the D swap. And then you make negative the other two entries. So I'll just keep that so that you know what I'm doing here. First thing I'm going to do is do the determinant. So I'll multiply down here 4e to the 3t times e to the negative 3t is very nice because the e's cancel out and I'll just get 4. Now you've got to go plus this way. Once again, the e to the negative 3's cancel. I'll get plus 2. And then I'll go ahead and do like I did before. I swap those diagonals. And then I negate the other two diagonals. So there we have it. Now I'm prepared to get my solution. That equals phi times the integral phi inverse f dt. Now phi inverse, I'll go ahead and replace it. I'm going to pull the 1/6 out front. You can do that with integration. So I'll pull the 1/6. I'll fill in the entries for phi when I'm ready for them. Right now, though, I am ready for phi inverse. And I'll have my e to the negative 3t, 2e to the negative 3t, negative e to the 3t, 4e to the 3t, and my f. My original f, let's take a look. Where was it? There it is right there. This portion is f. And you know what? I went and did this without thinking. I didn't even state the problem correctly. There was an x that was supposed to be there. This here is the f. So I have e to the negative t, te to the t. And let's go ahead. This is nothing but unpleasantness. But it has to be done. Unless your calculator has a computer algebra system and you're able to do all this with it, you're kind of forced to do it by hand, I guess. It's unpleasant, but so it is. I take this first row and multiply it by this column. So I have e to the negative 3t times e to the negative t of e to the negative 4t plus, and then I'll have 2e to the negative 3t times te to the t. So that looks like a 2t, this is plus, 2t e to the negative 2t And then I'll go to my next row. I have negative e to the 2t plus 4e to the 4t, or t e to the 4t dt. And now the integral just means I integrate every single entry with respect to t. So when I integrate e to the negative 4t, I'll get negative 1/4 e to the negative 4t. When I integrate e to the 2t, I will get negative 1/2 e to the 2t. Now here, I'm going to have to use integration by parts on each one of these pieces. Although they'll be very similar, so maybe it won't be so painful. When I go to integrate 2t e to the negative 2t dt, I'll do by parts, and I'll pull the 2 out front of there. So let me take it away from here. I'm going to use v and w because u was being used in this problem for something else. So when you do this, then this integral, let's see, I'll have negative 1/2 te to the negative 2t, but I got that 2 then. And then when you do the subtraction this way, you'll get a positive 1/2 e to the negative 2t, but there's a 2 in front of there. You don't need to worry about constants here. We are working on a particular solution. This will be negative t e to the negative 2t minus 1/2 e to the negative 2t. So I have minus t e to the negative 2t minus 1/2 e to the negative 2t. And then for this piece, the same kind of a thing happens, except I can imagine myself to have a 4 over here. I better not. I'll mess things up. So let me go ahead and do the calculation again. Here we're doing 4 t e to the 4t dt. I'll do the same things I did. So this integral, I'll have 1/4 t e to the 4t, but the 4 will squash the 1/4, so I'll get t e to the 4t. Then you have to do minus 1/4 e to the 4t, but the 4 quashed that again. And so we get t e to the 4t minus 1/4 e to the 4t. So all that stuff is secondary calculation, so I'll coordinate off. And let me go ahead and put this stuff in. Plus t e to the 4t minus 1/4 e to the 4t. Now here, to do my calculations, I am going to need more room. So all this stuff was equal to x sub p. Let me grab it. Remember, this is x p. The 1/6, I'll simply multiply it at the very end. Now my phi was 4e to the 3t, e to the 3t, and then negative 2 e to the negative 3t, e to the negative 3t, times, and then all this stuff. Now what I'm going to do before I do this calculation, these things are bad enough without having to play around with fractions and all that kind of stuff. I'm going to take out a negative 1/4. Or maybe I'll just take out a 1/4. And that way I'll put out a 1 over 24 here. That way I'll have a negative e to the negative 4t. This way I won't have fractions. In here I'll have a negative 4 t e to the negative 2t. Then I'll have a negative 2 e to the negative 2t. And then I'll have another negative 2. Then I'll have a 4. Then I'll have a minus 1. Well, I don't even need to write the 1. And I'm ready to multiply it all out. I probably should have taken out the negative 1/4 and gotten rid of a lot of negative signs, but no big deal. Let's see what we have. I need to do this row times this column, so my row. First I'll have 4e to the 3t times everything up here. So we'll start 4e to the 3t times negative e to the negative 4t. That'll be a negative 4e to the negative t. Next I'll have 4e to the 3t times negative 4e to the negative 2t. So that gives me negative 16 e to t e to the t. And then finally I have 4e to the 3t times negative 2e to the negative t. So I have negative 8 e to the t. And then I have to take this item here and multiply it times this entire second row. So that'll give me 4 e to the negative t plus 4 e to the negative t. And then I'll have negative 8 t e to the t. And then finally, I'll have 2e to the t. And now I do the whole thing again, but with this second row. So I'll start with e to the 3t times negative e to the negative 4t will be negative e to the negative t. And then I'll have it times the next thing, negative 12t e to the t. And then I'll have minus 2e to the t. And then I'll move on to these entries down here. I'll have negative 2e to the negative t. And then I'll have 4t e to the t. And then I'll have negative e to the t. Let me simplify where I can. All right, 4e to the negative t. I know I saw that. That's good. Those cancel each other out. Now what do I have for the t's? I have negative 24t e to the t. And then I have minus 6e to the t. And then down here I have negative 3e to the negative t. And then I have negative 12t plus 4t. Wait, let me slice these as I'm using them. I don't know why I have negative 12, but it's a 4. Negative 4 right there. This way, those cancel nicely. Now then it looks like negative 3e to the t. And there's no reason to simplify. I guess I could take out a negative, though. And we are good. That concludes the differential equations course.